I was trying to find the factory that made the wire. That's how this started. Not with a grand theory, not with a manifesto. I was sitting with a digitized archive of Victorian industrial records looking for one specific thing: the manufacturer of the copper wire used in the 1858 transatlantic telegraph cable. Simple question. Should have taken an afternoon. It didn't. Here's the number that started everything: 340,000 miles of copper wire. That's what the historical record claims was produced. Insulated, coiled, loaded, and laid across the floor of the Atlantic Ocean between 1856 and 1858. 340,000 miles. For context, that's the distance from Earth to the Moon and back, with miles to spare. We're told Victorian Britain manufactured this. We're told the ships carried it. We're told engineers designed the machinery to lay it in real time across 2,000 miles of open ocean. Sounds reasonable. Until you start looking for the receipts. Where was the factory? Which factory? Where are the parliamentary inspection records? Because Britain inspected its factories obsessively in this period. Where are the trade guild employment rolls, the copper import manifests, the insurance documents from Lloyd's? Not missing, not misfiled, gone. And here's where it gets genuinely strange. When I turn to the photographs, actual photographs taken on the deck of the SS Agamemnon during the 1858 laying operation, I found machines, large, complex, precisely engineered paying out engines, iron braking drums the size of carriages, equipment that would be remarkable in any era, equipment that appears in no manufacturer's catalog, no patent filing, no trade advertisement, anywhere. It's like finding an iPhone in a medieval cave. The object exists, you can see it, you can photograph it, but the factory that made it, the supply chain, the engineering drawings, the workers, simply isn't there. Either Victorian Britain possessed an undocumented industrial capacity that somehow escaped every trade record, every parliamentary survey, every factory inspector's report of the era, or the wire, and the machines that laid it came from somewhere we haven't been told about. There is no third option, and the wire is only the first anomaly. Because when I looked at the ocean floor survey that made the entire project possible, a survey conducted in 1856 with technology that, by every documented account, could not have produced it, the ground began to shift beneath the official explanation entirely. That's where we're going. Let's count. Let's return to the wire. Let's actually count 340,000 miles. We established that number. Now let's understand what producing it actually required, because the official version glosses over this part with remarkable speed. The decision to lay the cable was finalized in 1856. The cable was loaded onto ships in 1857. That gives us generously 18 months of manufacturing time. 18 months to produce 340,000 miles of copper wire. Let's turn on the calculator and just count. Divide 340,000 miles by 547 days. That's 621 miles of finished, insulated, coiled wire required every single day, every day, including Sundays, which Victorian factories did not work. So call it 730 miles per working day. The most interesting part is just beginning. Write in the comments what city you're from, and don't forget to hit like and subscribe. The tension is rising. Who's watching us from where? Drop a like and subscribe to the channel. There's more to come. Mark yourselves in the comments. Which country are you from? Hit that like button and subscribe. The plot thickens. Let's check our geography right where you are right now. Smash that thumbs up and subscribe. We're just warming up. Tell us, where are you watching from? Support the video with a like and hit that subscribe button. The climax is near. Share what corner of the world you're in right now. Drop a like and make sure to subscribe. Things are developing rapidly. Write your city in the chat, slam that like, and hit subscribe so you don't get lost. All the juiciest stuff is ahead. Let's get acquainted. Who's from where? Hit like and subscribe right now. The intrigue is building. Write where you're watching this episode from and reward us with a like and subscription. Emotions are off the charts. Quickly write what city you're from, drop a fat like, and subscribe to the channel. For comparison, the entire documented output of Britain's copper wire industry in 1850 across all manufacturers for all purposes was recorded by the Board of Trade at roughly 4,000 miles annually. That's everything. Telegraphs, electrical experiments, industrial uses, all of it. 4,000 miles per year. They needed 730 miles per day. Do you feel that dissonance? That's not a gap. That's not an inefficiency to be explained away by wartime production surge or private investment. That is a factor of 66. The project required 66 times the entire documented industrial capacity of Victorian Britain's copper wire sector. In 18 months. It's like asking a candle maker to supply electricity to modern Manhattan. The scale isn't just ambitious, it's categorically impossible within the documented framework. We're told British industry rose to the challenge. Sounds inspiring. But where are the emergency factory expansions? Where are the parliamentary labor requisition records? Where are the copper import surges in the trade ledgers? Because Britain didn't mine its own copper at this scale, it imported from Chile and Cornwall. We looked. The Institution of Electrical Engineers holds records from this period. Lloyd's Register documented industrial shipping. The Board of Trade published annual manufacturing surveys. The copper surge that should have been visible across all of them, isn't there? Either Britain secretly operated an undocumented copper wire manufacturing infrastructure 66 times larger than every official record indicates, or the wire was not manufactured in Britain in 1856 and 1857. There is no third option. This is not a rounding error. This is not a gap in the archive. This is a missing industrial civilization, one that produced 340,000 miles of wire and left no employment records, no factory footprint, no raw material trail. The wire exists. The factory does not. But the wire is almost the least strange part of this story. Because now we need to talk about the ships that carried it and the machines on their decks that nobody apparently ever built. Shift your gaze from the wire to the ships. Because what happened on those decks raises questions that no maritime historian has cleanly answered. The SS Agamemnon, the SS Niagara. These are the two vessels the historical record assigns to the 1858 cable-laying operation. Both were existing ships, a Royal Navy warship, and an American naval frigate selected and retrofitted specifically for this mission. We're told the retrofit took weeks. Let's understand what that retrofit actually required. To carry and deploy 5,000 tons of cable coil, that's the weight of roughly 3,500 family cars stacked on a ship's deck. The vessels needed structural reinforcement of their entire lower hull. They needed custom fabricated cable storage tanks built into the hold. They needed paying out machinery, enormous iron braking drums, precision dynamometers capable of measuring cable tension in real time at ocean depth, and mechanical governors to control deployment speed to within feet per minute. None of this equipment existed before this project. Who designed it? Where are the engineering drawings? Which foundry cast the iron drums? Which instrument maker produced the dynamometers? Devices of extraordinary precision for 1857? We looked. The patent records of Britain and the United States for 1854 through 1860 contain no filing matching this machinery, no foundry invoice, no engineering society publication describing the design process. The Institution of Electrical Engineers, which documented Victorian electrical infrastructure obsessively, holds no record of the paying out engine's development. A retrofit of this complexity on two ships simultaneously across two nations in weeks would today require months of engineering design, regulatory approval, and fabrication lead time. In 1857, with no precedent, no prior design, and no documented engineering process. Do you seriously believe this? It's like finding a fully assembled Saturn V rocket in a horse stable. The structure is there. The complexity is undeniable, but the engineering team, the manufacturing chain, the years of iterative design, none of it left a trace. Either the paying out machinery was designed and fabricated by an engineering tradition that kept no records, filed no patents, and employed no workers who later wrote memoirs, or the machinery arrived from somewhere outside the documented industrial history of 1857. There is no third option. The machines in the photographs have no origin story. They exist in images. They exist in the historical record as functional objects that successfully deployed a cable across an ocean, and they exist nowhere in the manufacturing history of their era. But here's what I haven't told you yet. When I looked at what those machines were actually deploying, the insulation surrounding the wire, the impossibility deepened in a way that made the engineering problem look simple. And here we approach the part that made me stop and sit quietly for a long time. The insulation. The copper wire we've been discussing couldn't simply lie bare on the ocean floor. Seawater conducts electricity. Without a perfect, unbroken insulating sheath along every inch of 340,000 miles of wire, the signal bleeds into the ocean and the entire project fails instantly. The insulation wasn't secondary, it was everything. The material they chose was gutta percha, a natural polymer harvested from trees in the Malayan jungle. Now let's trace what that actually required. The decision to use gutta percha was formalized in 1856. The cable was loaded in 1857, 18 months. In that window, someone had to identify and harvest sufficient resin from Malayan jungle trees. Each tree yields roughly 1 pound of usable gutta percha. Ship the raw resin to Britain across a 6-week ocean voyage, refine it into a workable compound, and then apply it to the wire at a perfectly consistent thickness under continuous mechanical tension. Let's count the trees. To insulate 340,000 miles of wire at the documented sheath thickness, engineers required approximately 250 tons of refined gutta percha. 1 tree, 1 pound. That's 500,000 trees, 500,000 jungle trees, hand-tapped in 18 months. Where are the plantation records? The shipping manifests from Singapore or Penang. The British Customs import logs that should show 250 tons of raw resin arriving at a British port? We looked. The Smithsonian Institution holds related natural history records from this period. Lloyd's documented cargo manifests obsessively. The Board of Trade tracked colonial resource imports with bureaucratic precision. The 250-ton gutta percha shipment that should have been one of the largest single botanical imports in Victorian history, isn't there? But here is where it becomes genuinely cold. The 1866 replacement cable, also gutta percha insulated, was retrieved from the ocean floor in sections during the 20th century. It had spent decades under 12,000 feet of water, under pressure that would crush an unprotected human body, in salt water, in darkness, at near-freezing temperatures. The insulation was intact. Modern polymer engineers, given the documented composition of Victorian gutta percha and the pressure and temperature conditions of the deep Atlantic, cannot fully account for this performance. The material shouldn't have lasted decades, it lasted generations. Either Victorian Britain accidentally formulated a deep-sea polymer compound that outperforms materials we deliberately engineer today, or the compound was not accidentally formulated at all. There is no third option. The ocean floor preserves something we can no longer explain, and the deeper we look at what made this project physically possible, the more the ground shifts, because we haven't yet discussed the map. And the map is where the official explanation doesn't just strain, it breaks. Look at the map. The actual 1856 bathymetric chart of the North Atlantic floor, produced by HMS Cyclops under the command of Lieutenant Matthew Maury. Look at it carefully. It shows a plateau, a relatively shallow, continuous ridge running between the coast of Ireland and Newfoundland, a natural underwater shelf that made the cable route possible by keeping the cable above the deepest, most crushing ocean trenches. Without this plateau, the project fails before it begins. The cable would descend into abyssal depths where no Victorian technology could follow. They called it the Telegraph Plateau. Convenient name, convenient discovery. Now let's understand how HMS Cyclops mapped it in 1856. The sounding technology of the period was this: a weighted hemp line dropped overboard, allowed to sink until it hit bottom, then retrieved by hand. One measurement. Hours of work per data point in deep water. The hemp line itself, and this is documented in contemporary Royal Navy survey complaints from other expeditions of the same era, broke under its own weight at depths exceeding 1,800 fathoms. The line simply couldn't support itself across that length. The Telegraph Plateau sits at depths between 1,500 and 2,000 fathoms, right at the boundary where the equipment documented as used by HMS Cyclops begins to fail. Let's count what a reliable survey actually required. To map a cable route across 1,686 nautical miles of ocean floor at sufficient resolution to identify a navigable plateau, not just guess at it, but chart it with enough confidence to commit millions of pounds and a transatlantic cable to it. You need data points roughly every 5 to 10 miles. Call it 250 measurements minimum. Each measurement in deep water. Lower the line. Wait for contact. Retrieve the line. In 2,000 fathom water, that retrieval alone takes 3 to 4 hours per sounding. 250 soundings. 4 hours each, that's 1,000 hours of continuous sounding operations. HMS Cyclops conducted its survey cruise in weeks, not months, weeks. Do you seriously believe this? It's like mapping the surface of Mars with a telescope from 1856 and then landing a rover on the exact coordinates you identified. The resolution of the results simply does not match the capability of the tool. Either HMS Cyclops possessed sounding technology substantially more advanced than anything documented in Royal Navy equipment records of the period, or the Telegraph Plateau was identified by a survey that predates HMS Cyclops. There is no third option. The map was too good for the tools that made it. And this matters beyond cartography, that because someone knew exactly where to lay the cable before the survey ship ever left port. But the map is only where the visible anomalies begin. The photographs are where they become impossible to dismiss. Now let's return to those photographs. The open loop from the very beginning of this investigation was the machinery on the deck of the SS Agamemnon that I mentioned and then deliberately set aside. It's time to close it. The photographs exist. This isn't speculation. They're held in archives, reproduced in Victorian illustrated newspapers, documented in the Illustrated London News coverage of the 1858 expedition. You can find them. Look right now if you want. Search SS Agamemnon cable laying 1858 deck photographs. What you'll see: paying out engines of extraordinary scale and mechanical complexity. Iron drums the diameter of a carriage wheel mounted on precision-machined frames, tension-measuring instruments, dynamometers integrated into the deployment system with what appears to be calibrated dial readouts, cable guide mechanisms that required exact geometric tolerancing to feed 340,000 miles of wire overboard at controlled speed without kinking, snapping, or tangling. We see the machines. We see them operating. We see sailors standing beside them for scale. What we don't see anywhere is who built them. I spent weeks searching. British patent records from 1850 through 1862, American patent records across the same window. French brevets d'invention, publications of the Institution of Civil Engineers, the Institution of Mechanical Engineers, and the Institution of Electrical Engineers, trade catalogs from the major Victorian ironworks, Maudslay Sons and Field, Penn and Sons, Napier and Sons, the firms that built the era's most complex marine machinery. Nothing, no filing, no catalog entry, no retrospective "we built the Agamemnon engines" advertisement, which Victorian manufacturers absolutely published when they wanted prestigious clients. Silence from every source. Industrial manufacturers of the 1850s were not modest. They advertised in engineering journals. They exhibited at international exhibitions. They named their machines after naval victories and aristocrats. If a British firm had built the paying out engines for the most celebrated engineering project of the Victorian age, a project that Queen Victoria herself sent a congratulatory telegram over, that firm would have announced it from every available platform. Not one did. It's like finding a functioning MRI machine in a 19th century hospital. You can photograph it, you can document that it worked, but the supply chain, the physics knowledge, the manufacturing precision, the calibration instruments belongs to a different era entirely. Either a British or American engineering firm built this machinery and then, uniquely in Victorian industrial history, maintained absolute silence about it forever, or the machinery was not built by any firm operating within the documented industrial framework of 1857. Photographs, actual photographic evidence of machines nobody made. This is not a gap in the record. This is the record telling us something we haven't been willing to hear. And when you zoom out from these photographs, when you stop looking at one ship and look at the entire planet in the same 8-year window, what you find will make this feel like a minor footnote. Step back from the Atlantic entirely. Pull the map wide. Because the second open loop, the one I planted at the beginning and haven't closed yet, lives here at planetary scale. Here is the fact. In an 8-year window, 1851 to 1859, 12 separate nations on 6 continents began laying submarine and overland telegraph cable infrastructure simultaneously, not sequentially, not in a chain of inspiration and imitation. Simultaneously, Britain, France, Prussia, the Ottoman Empire, British India, Australia, Cuba, Brazil, the United States, Canada, Egypt, the Dutch East Indies, 12 engineering traditions, 12 separate institutional decisions, 12 independent supply chains, supposedly. We're told this was the natural diffusion of a good idea. One nation demonstrated the technology, others followed. Sounds reasonable, until you look at the dates. The first successful submarine cable crossed the English Channel in 1851. By 1852, cables were being laid in the Ottoman Empire. By 1853 in India. By 1855 in Australia. The diffusion from demonstration to independent deployment across 6 continents happened in under 4 years, in an era when a letter from London to Sydney took 3 months by ship. How does engineering knowledge that complex, knowledge we've now established had no documented manufacturing base even in Britain, travel faster than a letter? Ask yourself that, sit with it, and now the detail that made the hair on my arms stand up. The gutta percha insulation compound, the material with the unexplained deep-sea performance characteristics we examined in Part 4, appears in all 12 networks. Not a similar compound, not a regional variant, the same material specification, the same application method, the same documented performance characteristics across 6 continents deployed by 12 nations that had no documented communication fast enough to share a formula. We see the same insulation, we see the same machinery design vocabulary in regional cable-laying photographs from Australia and Cuba and India. We see the same paying out engine architecture, the same iron drum geometry, the same tension management approach in images from operations that supposedly developed their equipment independently. It's like discovering that 12 isolated medieval villages, with no contact between them, all independently invented the same specific smartphone model, down to the charging port. Either 12 nations independently arrived at identical technical solutions to identical engineering problems using identical materials, with no documented communication pathway fast enough to explain the synchrony, or a single coordinating source distributed pre-existing knowledge to all 12 simultaneously. The pattern repeats with unsettling precision. This is not a coincidence. 1 is a coincidence. 2 is a pattern. 12. Across 6 continents in 8 years with identical materials, that is a system. And when you understand it as a system, when you ask who operated that system and from where, the question that started this investigation, the simple question about one copper wire factory, suddenly feels very different. Let's focus the lens on one specific individual. Because within this system, this coordinated planetary-scale infrastructure deployment with no documented manufacturing base, there is a man whose role the official version has never adequately explained. Cyrus Field, American businessman, paper merchant by trade. We're told Field was the visionary financier who drove the transatlantic cable project from concept to completion. He raised the capital, he organized the expeditions. He personally persisted through 3 failed attempts before the 1866 permanent cable succeeded. An inspiring story of entrepreneurial determination. Here is what that story requires us to accept. A paper merchant, not an engineer, not a physicist, not a naval architect, coordinated the simultaneous resolution of at least 5 distinct categories of unsolved engineering problems: deep-sea cable manufacturing, hull structural modification for 5,000-ton payloads, precision paying out machinery, deep ocean insulation chemistry, and mid-ocean bathymetric navigation. He did this across two nations with no engineering degree, no documented technical training, and no prior infrastructure project of any scale. Who told him it was possible? Where did the technical specifications originate? Lord Kelvin, William Thomson, the actual signal physicist on the project, later described the cable's electrical behavior in terms that required theoretical frameworks he himself was still developing during the laying operation. He was solving the physics in real time, yet the cable was already built to specifications that his emerging theory would eventually justify. The engineering preceded the science that explained it. It's like building a functional airplane in 1850 and then waiting for aerodynamics to be invented to understand why it flew. The object worked. The theoretical framework to design it didn't exist yet. Either Cyrus Field possessed undocumented technical knowledge far beyond his biographical record, or Field was the public face of a project whose actual technical direction came from a source we have not been told about. There is no third option. We're told Field was the dreamer and Kelvin was the genius. Sounds like a good story. But dreamers don't write cable electrical specifications, and geniuses don't validate engineering that runs ahead of their own published theory. Someone knew the answers before anyone had formally asked the questions. This is not a gap in one man's biography. This is the same pattern we've now traced across wire manufacturing, ship retrofitting, insulation chemistry, ocean floor cartography, photographic machinery, and planetary synchrony. Every thread leads to the same absence, a missing source, a knowledge origin that the official record simply does not contain. We've been looking at the edges of a shadow. We haven't yet looked directly at what's casting it, because when we examine what happened on August 5th, 1858, and the day the first message crossed the Atlantic, the timeline reveals something that should have been impossible even given everything we've